Hello Year 13, hope you're all doing well. This is the video for exercise 4D of the Moments chapter. We've covered most of the content, that's the basic stuff. We just need to do a few more examples where the modelling assumptions that we've been used to up until now aren't quite going to be the same. We're going to introduce new assumptions on our model. So, up until now we have covered examples where the rod that we've been using has been uniform, and in that case our assumption is that the weight of the plank goes right in the middle of the rod. But this time it might not be the case. We're going to look at non-uniform bodies where we're going to vary where the centre of mass and the weight is going to go. Okay, so here's our first example. Sam and Tamsin, they're sitting on a non-uniform plank, AB, practicing their social distancing. The plank's mass is 25 kilograms and the length is 4 meters. There's a pivot on our plank, and all of this is going to go on the picture in a second. M is at the midpoint, that's where the pivot goes, and the centre of mass isn't in the midpoint, it's off to the left, where AC is 1.8 meters. Okay, here's the picture. AB, pivot is M, normal reaction force at M, and then C, that's where our centre of mass for our plank goes, 25G. And then we can put some extra little distances on. And then here's Tamsin sitting on the end at A, that's her weight, 25G. And then Sam has mass 35 kilograms, the weight therefore is 35G, but we don't know what the distance is where that should go, and that's what we're trying to find out. So we're going to use moments, and we're also going to use the fact that this is in equilibrium to work out what's going on in this picture and how far Sam should sit. Okay, so we're going to call the distance x from M to where Sam sits, and then we're going to take some moments, but if we're clever about where we take moments from, we can greatly simplify our calculations. We can greatly reduce the work we've got to do. So what we're going to do, we're going to take moments about M, because, as we've seen in a previous example, the normal reaction force goes through that pivot point of M, and so we're going to get a moment of 0, and our Rm is not going to appear in the calculation. So we're going to take moments about there. Okay, and as you can see, there's 3 moments to consider. We're going to number them up, we're going to calculate them, and then with some algebra we can figure out x. So moment number 1, the red one, distance times force, 2 times 25G, 50G. Anti-clockwise is the direction. Moment number 2, second force there in the middle, times the distance, 0.2 times 25G is 5G, and that's another anti-clockwise moment. And then on the other side, the third moment is x by 35G, but this is in the opposite direction. It's clockwise 35GX, and our aim is to solve for x. Now to do it, our body is in equilibrium, nothing is kind of rotating around, nobody's falling off, nothing like that, so it's in equilibrium, everything's balanced. So we're going to equate the clockwise moment with the anti-clockwise moment. Those are the anti-clockwise ones. We can add them together. It's equaling the clockwise moment over there. And then it's just a matter of solving the equation. So collect the left-hand side, looks like. 55G over there. G's on both sides, so we can cancel those out. So we have 55 equals 35x. Divide by the 35, and our answer is 1.57. Okay, so with a bit of looking at what's going on in the picture at the end, with a bit of interpreting, x is 1.57, but that's not actually what we want. We want to know how far from A we're sitting. So don't forget to add that 2 meters on as well. That's AC plus C to M. So actually 3.57 meters instead. Okay, it's also important to look at what happens in the picture. Okay, one more example. Let's have another look. 3 meter long rod AB, the weight's 20 newtons. Horizontally, most of these moments questions will be horizontal. Resting on supports at C and D, we're told some distances to the supports. We've also got information about the reactions, the reaction forces on each of these pivots. And then we want the distance of the centre of mass of the rod from A. So where does the centre of mass, the weight of the rod, go? Okay, there's the picture. We're told information about AC and DB, so we can get those. Those distances can go on. Then normal reaction force at C, normal reaction force at D. Okay, roughly put on where the centre of mass is going to go. If we're in the wrong place, it doesn't matter, it just means there's more interpreting at the end to figure out where it's supposed to go. From the information over there in red, we can simplify what we've got for our R's. So we know that RC is 3 lots of RD, so let's replace it. Okay. Now we're in a position to find the normal reactions because our body's in equilibrium. We can equate the upwards forces with the downwards forces and easily solve for R. So upwards, 4 lots of RD and then downwards equals 20. RD is 5. Okay, calculate, put them on. 15 newtons, 5 newtons. Okay, now we can do some moments. I want to know how far away that 20 newtons is from A. So we should put an X maybe on it. And then when we do our moments, we're going to use little x for that distance there. Okay, number up the moments. We're going to calculate from A, because that's going to make the calculation easier, because we're doing the distance from A. Might as well do that. Moment number 1, write it down. Second moment, we've got an unknown x, but it's times 20. That's clockwise. And the third moment is about to appear as well. Okay, same as before, equate the anti-clockwise with the clockwise. That's the sum of the anti-clockwise. That's the sum of the clockwise. And solve. Group the terms, divide, done. So the centre of mass is 1.38 meters. Okay, just with a quick check, just make sure you've fully answered what the question wants.